Okay, we are starting Unit 4 now, and Unit 4 is about the properties of polygons. A lot of 4.1 is review from Unit 3, so I'm going to skip through it pretty quickly. A couple of new terms are concave and convex. Now, basically, these are defined best by the pictures. A convex polygon is a polygon so that if you draw a line segment across it, the segment will always stay on the interior of the polygon. A convex or a concave polygon has a dent in it, so that if I go to draw that same segment across a polygon, I slip outside of the polygon. And that's the difference between concave and convex. When we talk about formulas and things that we are doing, we are always going to be using convex polygons. Our angle sums and interior and exterior sum theorems don't work on concave polygons. They have their own set of rules. So just very quickly, this is convex, convex. This one is concave because I can draw that segment from here to here and go outside. This is also concave. It's got a dent in it, and this one is convex. So just a quick, simple thing that you probably saw in elementary school. Regular polygons is a review term from Unit 3, all sides and all angles are equal. So if we have a sum, we can divide it up equally amongst everything. Regular polygons make all of our formulas very easy. Interior angle sum is also a review from Unit 3. The sum of all of them is 180 times n minus 2, where n is the number of sides. One interior angle can be found by taking the sum of all of them, 180 times n minus 2, and dividing by the number of sides. And that's how we find one interior angle. Now the exterior angle sum, remember that was our trick question, because for any polygon, the sum of the exterior angles is always 360, no matter what size polygon we have. Now, for a regular polygon, and that's where that regular comes in, one exterior angle is 360 divided by n, where n is the number of sides again. Those were review terms. Now, these three questions really work best if you just work from the picture first. Whenever we have a picture with interior and exterior angles, remember that that linear pair idea is very powerful. These two angles I marked in green form a linear pair, so this one has to be 110. These two are a linear pair, so 120. These two are a linear pair, so this is 115. Here's my linear pair, 140. Now when we get over to this last one, we don't know the interior or exterior angle, so we get kind of stumped. But if we remember that the sum of all exterior angles has to add up to 360, and I look at my exterior angles, which I've marked in yellow, I see I'm only missing one of them. So if I call that A, my exterior angle, which happens to be my first problem here, would be 360 is equal to 70 plus 60 plus 65 plus 40 plus the angle I don't know. And when you work that math out, A ends up being 125 degrees. Now using the linear pair, that makes this angle 55. As a nice check, these interior angles of a 1, 2, 3, 4, 5-sided figure should add up to 540. So if I check, I should never get this kind of a problem wrong, because There are multiple ways to check. And so it does work out correctly. The sum of the interior angles of the polygon, it's a pentagon. And if you don't just remember at this point that a pentagon is 540, we take 180 and 5 minus 2, which is 540. And then we ask for the measure of each interior angle. Because we worked on the picture, that one is already done. Now the measures of x, y, w, and z at first look kind of hard to figure out. But I see parallel lines. And as soon as I see parallel lines, I know that I have angles. I have corresponding angles, I have same side interior, I have all those angle relationships. So if I use the green line as my transversal, 110 and y are corresponding. So I can use parallel implies corresponding. Then I can use the linear pair idea for w, and that ended up being 70. W and x are corresponding, or x and y are a linear pair. So that makes that also 70. Now we can either figure out z by taking quadrilateral sum of 110 plus 90 plus z plus 70 equals 360, or we can switch and look at this as our transversal, and now we have same side interior angles, which are supplementary, which means that z has to be 90. So multiple ways to check your answers. Again, I could check it by saying 90 plus 70 plus 110 plus 90 better equal 360. And our last review problem here, given a regular keyword heptagon, 7 sides, the measure of one interior angle. So I have 180 times 7 minus 2 divided by 7. And one angle ends up being 128.6 degrees. It's okay to have a decimal or fractional angle measurement. Where we can't get fractions is in a problem like number 6. Now this is a similar problem to what I've asked you. In Unit 3, I ask you, how many sides does it have? I ask you to figure it out. Now I'm asking you, can it be a regular polygon? And the key here is that n must be a whole number, because it is the number of sides. I can't have a fractional number of sides. I can have a fractional or a decimal length, but not number of sides. So I'm going to set up my interior angle sum formula, 180 times the number of sides I don't know, divided by 2, all over the number of sides. And I'm going to say with a question mark, does that equal 135? If I solve this and work it out, and n is a whole number, it can be a regular polygon, and I'll know which one. If it ends up being a decimal or a fraction, it cannot be a regular polygon. So the first thing to do to get that n out of the denominator is to multiply both sides by n. Now I'm going to do the distributive property. Subtract 180 from both sides. Be careful to keep track of your negatives, because that is one of the biggest places where kids make mistakes. Remember, you can't have a negative number of sides either. Divide both sides by 45. Therefore, this is a regular octagon because it worked out evenly. That is it for lesson 4.1. Like I said, most of it is review. The first homework assignment is combined 4.1, 4.2. So go ahead and give that assignment a try now.